Welcome, everybody. Let me start with the words you probably haven't heard during the whole DevOps. Let's talk about AI. Yeah, I'm joking there because, I'm genuinely thankful that after all that previous talks, you are still want to go through yet one AI-related presentation. Because, after the whole conference, I think everybody should get the honorary PhD in the topic. However, like we said, I will try to go with a bit different approach than the previous one. I hope you will like it. So now I've told you what you will be expecting to see. I will tell you what you can expect on the presentation. However, a few words about me. I'm Artur Skowronski. I'm head of Java Kotlin development in the Virtus Lab company. Do you use Scala? Or did you use Scala? Do we have any Scala users? Wonderful, because what you can know us from is the fact that we are the current steward of the Scala. Apart of that, I'm the editor of the JVM weekly newsletter. If you will like what you will see today, let's subscribe. And now, as we do not have that much time, let's go strictly to the topic of the presentation. Because I mentioned AI. AI is in the topic of the presentation. But there is a question, what AI I will be talking about? Because AI means different things for different people. So, for setting the stage. First thing, what we won't be talking about today. There won't be nothing about the using LLM through API. There was already a lot session about that particular topic. We won't be talking about data engineering, out of scope, as well as model development. I'm not the ML engineer. I don't feel comfortable enough to talk about that particular piece. What we will be talking about is about the usage and inference from existing models, mainly about the GPU programming. But I know that if I told you that it will be a presentation about the GPU programming, nobody would come. So that was a trap, sorry for that. Still, I hope you will like it. OK, one more important disclaimer. Everything will be helicopter view, so we won't go particularly deep into any topic. However, I will just give you a like I said, helicopter view of everything that is happening currently in the JVM space connected to the using a big machine learning models. One yet important information, I have 152 slides for 45 minutes. So don't turn your back, don't look away, and don't blink, because otherwise you won't be able to keep up. And having done everything, let's start the presentation. And we'll start with a bit of theory. Because what the inference really means, not everybody knows what the inference means. OK, so we have already some people who deserve that PhD, but for the rest, I will have a bit of the introduction. Because whenever we have model, in truth, we have some kind of the data structure that was already exposed to a lot of different examples. And based on that examples, it just created the internal shape through the multiple parameters that is able, when presented with new data, to do so-called inference. Inference means that we are just presenting the already trained model with the new data and making the prediction. Because what machine learning models are doing, they are doing the prediction. Such model, when we are going to the inference, we are having, each model has multiple layers. On each of those layers, we are going through the handful of different calculations, a lot of those. We can imagine inference as the process of just doing the calculation through multiple layers to achieve the result. It can be next token of text classification, of image, of any other thing. And in practice, such inference is done not by hand, but through the special frameworks, like, for example, TensorFlow. That's why TensorFlow is such popular today, and everybody tries to be expert in it. But there's no only TensorFlow. We have also different frameworks, like Keras, that has its own kind of models, H5. We have scikit-learn, that is using Python models. We have PyTorch. We have TensorFlow. All of them have a bit different approach to the topic, but they have something in common. They are all written in Python. That's why most of the current machine learning development is happening in Python, because the whole ecosystem tends to go into that direction. Python was quite popular in the academic research and that community, the tools coming from that community. That's why everybody wants to learn Python in 2024. However, if we already have a lot of different tools that are already written in Python, but we are Java developer, probably we do not want to write Python. For example, my soul is not allowing me to do that. I never liked the language. So maybe, as there are already some components, let's think about using them through our Java code. Because probably for some people who already attended some presentation during DevOps, that is currently possible. It is possible through the project that is called GraalVM. I assume most of you heard about the GraalVM. However, most of the developers that associate the term, from my experience, are associating with the native image. So ability to build smaller, leaner, faster application. That's not the GraalVM I will be talking about today. Because GraalVM originally started not as the native image solution, but as the one VM to rule them all. And what is that? What does it mean, apart of being the wonderful Lord of the Rings reference? It means, to explain, I will use the other example. We have JVM. And for the JVM, you can have different languages that are running on that particular piece of the infrastructure. We have Kotlin, we have Scala, we have Groovy. Each of those languages can be considered a bit of syntax sugar over the JVM. I know that Scala people hate when I'm calling their language syntax sugar. However, it is what it is. So what the GraalVM wants to achieve, it wants to be VM. If you can run multiple languages on the JVM, let's have the virtual machine that can run all the languages. Ladies and gentlemen, GraalVM. That was the approach to the topic, and it is connected to the yet another very interesting paper, self-optimizing AST interpreters, so it's better known as a truffle. And what truffle is allowing us to do, it's allowing us to create the language interpreters that will be run on the Graal compiler in a way that we can just introduce runtime of the other languages to our JVM code. And currently, language interpreters can be treated, they are just distributed, language interpreters written through the truffle. They are they are delivered through the special dependencies from the Maven Central, classic dependencies from the Maven Central. So we can have GraalPy runtime, GraalJS runtime, GraalRuby runtime, or even Java runtime in the GraalVM written in the, using the truffle, simply from the Maven Central. In practice, it looks like that. So we have a piece of the standard Java code that are presented with a piece of the Python code, and that Python code can just run the computation that will be returned to our Java code. Simple. This is an example that was taken strictly from the GraalVM examples. We can open AI there, we can do the call, we can just consume all those dependencies that were already created. So the case is closed. We can just use all those Python stuff, yeah? Unfortunately, it's not always that easy, and it's never that easy. Because the truth is, what is the power of Python is the fact that it's mainly the interface. Because all the heavy lifting, all the machine learning stuff, computation, they are not done through Python. Python is pretty slow. They are done in C++. And to be able to connect from the GraalPy to the C++, you need to do a few hops. GraalPy currently have access to the native extensions, so they are able to just take that C code that was already used to run all the Python magic and compile it. However, it needs to be precompiled, it needs to be distributed, it needs to be there. It's not easy to just run the code and call it a day. Currently, GraalVM and Truffle are going in that particular direction, and compatibility is growing with each new distribution. For example, the one from the March this year, as you see there, they are introducing support for the TensorFlow, they are introducing support for the PyTorch, so framework you have seen on the previous slides. However, still, compatibility is not perfect. There is still a lot of packages that are not tested and not compatible. So whenever you are trying to run the production project, there are problems. So for now, I think that we can say that just simply running Python, while is possible, and the support is getting better, it's not the recommended solution. It's the faster solution, but not the best one. That's why If you want to learn a bit more about the GraalPy, yesterday there was the session about it. As far as I know, it wasn't available yet during the morning on the Devox channel. However, probably it will be today. So it will bring you a lot of details about how GraalPy works. OK, let's carry on. Because as we already discussed that Python is not the best solution, let's do inference of models from the pure Java. And this pureness is, OK, I will take into the quote. You will understand why in a moment. Model inference can be done in Java through like we have Python frameworks. We have also Java frameworks, and we have a lot of those. We have TensorFlow. There's Java TensorFlow ready for us to use. We have deep learning for J, and this was the framework I have been able to use before all those ChatGPT craze. It was the standard solution for a time. There's Tribuo that was delivered by Oracle, and also around Java JDK 16, something like that, if I remember correctly. A lot of different projects. Problem with them is that each of those has totally different API. Because the machine learning community is changing very quickly, and it's very hard to create something standardized. However, because if somebody creates the standard, there's a problem that not everybody wants to implement it because they have new ideas that they want to test. It's hard to do that with this totally standardized way. However, the truth is that even while this XKCD comics is true in most cases, it wasn't always the case with Java. Java was pretty good in creating standards. And everybody should probably like no other community. Because, most of the APIs we are using, they are standardized. We have JPA, Hibernate, Eclipse Link, OpenJPA. We have JDBC, PostgreSQL, MySQL, Oracle database. JAX-RS, also multiple implementation, not talking about the server API. There is a lot of stuff like that. And in the past, such specifications were created through the Java specification request. And this is not just the standards or things of the past. Last week was announced that Spring 7 will try to migrate to JSpecify. So new standard, community standard was created for the null values handling in Java. It was announced that Spring will try go that direction. So it is happening. Standards are happening all the time in Java. We have, through the JSR project, we achieved a lot of different stuff, like you see there. You probably recollect most of the names here. However, not the first one, I assume. Because the first one is Visual Recognition Visual API, and this is the closest we get to having the standardized API for the Java. It was created a few years ago. The reference implementation is DeepNet. There's also Deep Java library created by Amazon. However, you could assume that in the today's machine learning craze that is happening around the world, you would hear about it in the past. And for most people, it isn't the case. Why? Because it was created a few years ago, and it was created for a totally different world. As you see, let's just go to the list of examples. What we have there? We have linear regression. We have logistic regression. We have classification of images. We have the handwriting recognitions. Not something that most of the people think about when they are thinking about LLMs and machine learning in 2024. You are probably right with that. So nobody cares, because that's not the standard everybody wants to have. And that's the one problem. The standard was created prematurely a bit, or for the different use case. The other problem is that I already mentioned. It's very hard to create something common in the machine learning space because changes are happening monthly. There, of course, there's some standards that are trying to making models more general. ONNX is one of them, Onyx. However, the different standards, different kinds of the models are there for purpose. The purpose is performance. Because what is the most crucial part whenever we are doing the calculation and we are doing any work with machine learning, the performance is a key there. Because in each of those layers, we have a lot of computational complexity, because each layer requires performing a vast number of mathematical operations, like matrix multiplication. And the bigger the model is, the more layer we have, the greater is number of such operations. So we need to calculate very, very fast, and the architecture of the model matters depending on what models we use and what use case we have. There's also problem with the model size. The models are getting bigger and bigger. They have more millions, billions parameters. And processing them, storing of them, and even feeding the memory with them, it's very hard problem that requires significant memory resources. And we'll start with optimization for the second case, because now it's time to talk a bit about the project Valhalla and half floats that are coming with it. Because to tell what are the half floats, let's mention the standard floats that you probably all heard about. And being more precise, the floats everybody is using are floats 32, because they are made from the 32 different bits. 1 bit is for the sign, positive or negative. The 8 bits means the exponent range. So what is the smallest possible float and what is the biggest possible float? And 22 bits are fundamentals of precision. How many floats can be put into a particular range? So between 1 and 2, how many different values we can have? And for float 16, we are going, the standard is introducing smaller, so the range is narrower. So we are not able to store that big and that small floats, and also they are less precise. So between 1 and 2, we can just store less amount of values. However, for the machine learning models, most of the cases, it's OK. We can live with that problem, and we have half the memory used. However, and currently Valhalla, as you will see the list of the commits, it's checked on the 21st of September. I don't know if it's still the case. Maybe they are already merged. I do not believe that. However, I should check before the presentation. However, it's exactly what is happening currently in Valhalla. They want to introduce the half floats. This is happening right now. This is the list of commits from their repo. Of course, half floats are not the silver bullet. They can help. However, that's not the biggest problem. The vast amount of memory is not the biggest problem you have with machine learning models. It's important because it's the real cost. However, most of the times it's easy to add yet another brick of RAM, and you can live with that. The problem is that access to memory is important as well. You need to feed that information to the models pretty quickly. And for that, we'll need to go through yet another topic. There will be multiple topics during that presentation, as I mentioned, native calls. And you remember that meme, you remember that joke. We are laughing on the Python's developers that they are relying on the C++ programmers. However, we need to remember we live in that community as well. For one thing, the JVM, the standard one, not the GraalVM, is written in the C++. However, also, we are using a lot of the interoperability with C. Let's just take a look on the deep learning for J I mentioned before. As you will see, I hope you see, they love the screens in the DevOps rooms. Yeah. The truth is that deep learning for G is the layer over the C code as well, because all the memory handling is drawn through the GNI calls. There is also mention of something called NDRIs. We'll be back on this topic. This is important. This is something that is also used. However, let's stick with the GNI. Who have ever used the GNI? Java native interface. A lot of people. Who like writing GNI code? OK. I will need to talk with you guys. Please come to me after the presentation. Yeah, because JNI is the standard that allows Java to interoperate with the C and C++ from the beginning. It was created close from the beginning of Java, because it was introduced in Java 1.1 in 1997, when MacBooks looked like that. You know what? They looked pretty nice. I expect something worse when I was looking for the picture. And the reason why there was a lot of people who have been writing JNI, and that handful of people who just want to like it, there are reasons for that. For those who have never tried JNI, it will be the very quick introduction. Because whenever you are need to declare the native method in Java, you need to go through the very huge process. The first thing, you need to declare the method native. So you need to have such interface created, compile it to the code, and have the class file. Then you need to use one Java header tools, if you have it, yeah? Generate the C++ file header. Then you need to introduce the whole C++ method, compile by hand manually, compile it to the specific native file, and load it. This is very cumbersome process. And it probably was something we could live with in the world when the new version of the libraries was just delivered with the new version of the operating system once 3-4 years. However, let's just look on the release notes of CUDA. Their new version of CUDA, so the most popular, okay, we can assume is most popular GPU calculating framework, each month. It's happening a lot, and in this space, things are happening very, very often. That's why we need to have some better tools to be able to do interoperability with C, considering what is happening right now. That's why we need to introduce yet another project, the project Panama. Who have heard about the project Panama? Wonderful. I love the public here, because it's not always that obvious. So Project Panama is Project Panama, so the project that's goal is to introduce better interoperability with the 4-inch memory, 4-inch functions, and some other stuff in JVM. They introduced a tool that is called JXStat that automates most of the stuff that you have seen before. So they are creating the bindings, they are creating the headers, they are just wrapping the C++ library in it. You are to create the new version of library, you just need to rerun the JXStat. It's not the painless. It's not painless. However, it's much, much easier than it was in the past. It's a very good tool. However, it's not the only thing that is coming with Project Panama. We have also 4-inch functions and memory API. We have linker API, 4-inch data layout API, stuff we won't be covering today. But also, we have something called vector API. And this piece of code is very, very interesting. Okay, this is the first to introduce you why. This is the first time during this presentation when we'll be presenting GPU. It's not the last one. Because most of those frameworks that I presented to you, TensorFlows and others, they are run on the GPUs. They are based on the GPUs. Because GPU, as it will be stated a bit before, but the spoiler, it's very good in calculating the layers of the machine learning models. However, that's the reason why NVIDIA stock just go to the moon. First they have the cryptocurrencies, now they have the machine learning models. They are living in the wonderful economy for themselves. However, the truth is most of our machines at the current state, they are CPU-based. So it would be nice to have some tools that will allow us to run models on the CPU machines as well. And here, to introduce you to that topic, I will need to bring yet another term. Once again, we are on the DevOps. Everybody probably heard it already. Llama. Have you heard about the Llama? Llama is the open source models that was delivered by the Facebook, their competition of the GPT models from the OpenAI, and the one that is available in the public. So everybody can tinker with it. And if you can tinker with it, tinkerers will come. And the reason why it's pretty interesting is the fact that, and the tinkerers, most of the cases of the tinkerers started to think, okay, maybe we can, as the TensorFlow is just the piece of our application that run on the GPU and is made for the GPU, maybe we can bring something that will work well on the CPU workloads. And for Llama, the projects was created. There were two projects created. One of them, Llama 2C, was created by Andrej Karpathy, one of the probably best educators in the LLMs machine learning world nowadays. There's also Llama CPP that was created by Greg Brandstorm. Oh my God, I should have wrote down his name. However, a guy from the OpenAI. And what those two projects brings? They bring the single file implementation of the whole TensorFlow and the whole inference project. Now, it's just the single file run, in this case, it runs C, that is able to do the whole inference process without having to introduce any very broad frameworks. Because, the truth is that beauty of machine learning models is due to the fact that they are very, very easy. They are very computational heavy. You need to use a lot of energy for that. You need to use a computing power for that. However, what you are mainly doing, you are doing a lot of arithmetical matrix computation on each of the layers. So this is something that if we have CPU-based implementation, and Llama-C and Llama-C++ were CPU-based implementations, you can just add this file to your project and be able to calculate, do the prediction, do the inference. Of course, if there is code written in C, soon there will be code written in Java, because it works that way. And the first approach to the problem was to create the Java bindings. And Java bindings, there is a project for that. It's called Java Llama CCPP. So it's just the pre-made headers for the Llama project, because that was the easiest way. However, the easiest way is not always the most fun way. And we also have projects like Llama 3. Llama 3 Java. And this is project that, as we already mentioned, you are able to create the whole inference process in the single C++ file. You can do it also in single Java file. And it was done by the Alfonso Petersen, who is working in the GraalVM team. And today, at the first 50 p.m., you'll have opportunity to see the presentation about that particular topic. So how they did that, how it works, he's from the GraalVM team, so you can expect a lot of technical details. Unfortunately, I do not have time for technical details, so I need to carry on. There are, of course, other projects, for example, JLlama, a modern LLM inference engine for Java. It was created by Jake Luciani from DataStax. Also, there is presentation about the topic today. We are on the DevOps, like I already said. So you have presentation about each of those projects. Yeah, and the fact with JLlama is that at least a year ago, I do not have performance benchmark right now. It was very, very quick, comparable to the C++ implementation, even being better. And they are, how they made this that fast? Through the yet one interesting project that is happening in the JDK space, that is joining the Valhalla and Panama together. Project Vector API that is introducing themed instructions to the Java. And to understand what themed instructions are, so single input, multiple data, we need to understand first what single input, single data instructions run off. Of course, simplifications, because you see, we are talking about the hardware and we have just a few of blocks. However, it should give you an idea how it works. In the single input, single data model, we have, whenever we are running instruction on the particular piece of data, so doing some kind of the calculation, we are able to, we need to do it piece by piece. So for each piece of data, we need to introduce yet another, we need to rerun it once again. For the single model, single input, multiple data, the approach is a bit different. We are just batching our data set that if there's single instruction, we can run it on the same time on more than one data, more than the one data piece. And it's much, much quicker. And the truth is that JDK is doing that for us. OK, it's visible, because I wasn't sure. Whenever we are having the any loop in our code, JIT compiler, just-in-time compiler, is trying to optimize it in the process called auto-vectorization. And auto-vectorization is trying to change the execution of the code from the single input, single data to single input, multiple data, because that is just more performant, and they are quite good at that. However, it's not perfect. It cannot just handle all the cases. That's why Vector API was introduced. Vector API is the API that goal is to give the developers ability to simply go through all those, doing all that manually. So being in control when you want to vectorize your data and where not. As you probably see, the Vector API is currently in the F incubator. So we already have a lot of those. And the reason is it's waiting for Valhalla to be delivered. Because, like we said, it's the collaboration between Project Panama and Project Valhalla. Project Panama part is ready. Project Valhalla is not. And probably there will be some changes. However, API is mature and useful to that level that currently a lot of projects started to use it. They mentioned before projects, JLama for sure, Java, llama.java. I'm not sure because they want to go on the GraalVM, and GraalVM is not handling the vector API, so that probably is a bit more complex topic. I hope I will learn it during the presentation in the afternoon. However, JVector, like we see here, embedded vector search engine is currently using it. It's part, well, once again, something done by DataStax. It's the incubator API that is used in production because it's that useful, especially in the world when we are having the very big push into the machine learning models. So we need to do that. We need to use that incubation API because computational complexity matters. It matters because in those machine learning models, like I already mentioned, you need to do a lot of computation. And now, as the creme de la creme, we are finally going to the probably the most complex part, so talking about the special hardware. Because till now, we were just discussing the standard CPUs and standard workloads. Now, it's time to go a bit more crazy, because I don't know, doing the research for that presentation, for example, I learned that they were special multi-core chips created mostly for the enterprise computing for the Java. Azul did something like that in the past. I need to drop by to the booth to learn the story. However, most of the real production workloads is not happening on the standard CPUs. They are using different tools. And one of those we are already discussing about is the GPU. And GPU has, like I said, GPU has a time of its life because initially created for games and created in a way that you are able to calculate all the pixels in the spot. Then started to be used by the cryptocurrencies. Next, next day was introduced to the machine. Okay, it was always introduced in machine learning models. However, currently it's probably the most lucrative part of the whole industry. But that's not, because we have also different hardware that is, for example, TPU, so tensor processing units. That's one introduced by Google. We have also FPGA, so special programmable hardware that we can just make specifically efficient with a particular task. So a lot of different hardware that Java needs to handle. And now, why is it hard? It's time for the, once again, overly simplified example. If initially examples were simplified, now that one will be especially simplified. However, still I need to introduce that bit of logic because it will be necessary on the later part. Because whenever we are doing model inference run on the CPU, this is CPU in that case, we have just handful of cores. Even big CPUs, they have just multiple cores, and each core can handle one instruction. The instruction can have multiple data. We already mentioned that. We have some optimization like SIMD. However, we have just limited amount of cores. On the GPU, and they are just creating the result. On the GPU, we also have limited amount of cores, but we have millions of those. Because up to millions of those in the current machine. So we are able to calculate far more data pieces, far more kernels. I will explain what kernels in the moment, in the single run. So they are just, each operation on each instruction is very small. However, we need to run multiple of those. And a framework that was especially made for, and probably the glorious standard of the industry currently is CUDA. So the tool that was, the framework that was created for NVIDIA and made only for NVIDIA is the problem with all those hardware-based framework for the particular hardware. For example, NVIDIA is very careful to not allow anybody to run the CUDA on any other framework, on any other hardware, because that part of the business, CUDA is a vendor lock-in for the users. And this is a problem with all the hardware we'll be mentioning in a moment. And probably, and that's the model I would like to describe, because the CUDA model is one that becomes the industry standard. Because the problem, whenever we have millions of threads, and a lot of those, a lot of cores, is how you can be able to just feed them with data. You need to do it very efficiently because the memory barrier, just moving the place from the standard memory to the GPU, it's taking time and it's very problematic. That's one of the biggest bottlenecks. So the data structure that is used for that is called ND-grid. It's multidimensional grid. It can be 1D, 2D, 3D, because it was initially created for the video game, so being able to have a 3D data structure was important. Currently, it's in the simplification, it's just the matrix that can have a lot of different data pieces, a lot of different kernels fit to the GPU in the same time. And it is contained by the kernels, and kernel, it was probably the most surprising thing for me when I started learning about the GPU programming. Kernel has nothing to. Kernel is something that is a piece of code that is run on all those, this feed by the ND-grid to run on all those cores, okay, on the GPUs, in the simplification of the GPUs. And each thread runs the same data, same code, however, on the different data. That's how kernel works. And this way, GPU is able to parallelize as there's no limit. So they are able to parallelize the code far more than the CPU, even with the SIMD instruction is able to do. And the first approach, okay, so as we have theory behind us, let's talk about the Java implementation. And the first approach, how to handle with that topic, is to, okay, we have JNI, we have the CUDA, we have OpenCL that is used by the AMD hardware. Probably we can just run our JNI calls and be able to use C++ implementation. And as you see there, it's a bit similar approach what we have with the GraalPy. So we are having just the special handler that is able to take our CUDA kernel code as the string and pass it to the GPU. So it's working as the provider of the data to the GPU. It's something that works, and like I mentioned before, it's used, for example, for deep learning for J project. However, you need to maintain code written in the string. Not something we want to do, especially in the more complex project. So since the original idea that GPU will be something more than we expected at the start, there was, okay, the race. Who will be first to create the Java native API for that? And the first approach of expressing the kernels in Java code was Aparapi and Rootbeer, the two projects that wanted to handle separately CUDA and OpenCL. They didn't provide the NG-grid abstraction. You were just able, through the particular data abstraction called kernel, you were just able to provide the data, and all the heavy lifting were happening behind the scene. So Aparapi was for the CUDA, Rootbeer was for the OpenCL. They were separate projects because each of those could handle just the particular kind of hardware. The problem, there was a lot. The first one was lack of support for proper data types, because you could just use the kind of data that were available in the particular kernel infrastructure, and they were just strictly limited. Each of those projects support just one kind of hardware, so they were very vendor locky-ish. Also, the code they created, they was truly inefficient or required the manual hacks. Also, there were a problem with feeding the memory, because there's always a problem with feeding the memory whenever we are talking about GPU. As the ND-grid was not exposed directly to the developers, we couldn't control the process. We need to rely on the framework. So they weren't that fast. So the next approach was to go with something Java-specific as one of the projects. And the project was called Project Sumatra. And Project Sumatra took very very nice idea. It was executed after the JDK8. And whenever we are talking about the JDK8, we have streams, and we have something very interesting in our stream API. We have streams parallel. So the original idea of the Project Sumatra was, okay, maybe we'll be able to simply take parallelization on the stream and whenever possible run on a GPU, because we already have parallel structures. And that was original that was the idea, and it was working behind the scene. The idea is, okay, we have GraalVM because it was times GraalVM was already there, so we could use GraalVM to optimize that code and transpile it to the particular hardware. And it was a very good idea. However, the problem was that, once again, data transfer between JVM and GPU can reduce performance. It's the biggest problem, as you see to the whole presentation. Also, Sumatra approach relied on the GraalVM that much. It was not worth to execute the project because it was mainly just a bit of extension of the JDK of the GraalVM with its own problems. That's why the project was skipped. However, it will have the follow-up that we'll be talking at the end of presentation. I have 10 minutes. We are on the good time. Because now we need to go to the project that is live, TornadoVM. And TornadoVM, once again, is one of the probably most interesting projects in the community right now. Not well known, however, very interesting. Because what they want to achieve something like GraalVM, its simplification, but for the GPU. And they expose interesting API because they have task API that are just able to create a single kernel. We have annotation API, so if you want to just do some heavy lifting, GPU lifting on the single loop, we can just put the annotation and call it a day. And we have also something called Task Graph API. And Task Graph API allows us, and that's probably the most interesting part, to create the dependency with the particular tasks. So we can define, okay, we have a handful of tasks. We'll create them in the graph. And please now, TornadoVM, calculate them for us. Please remember, they are dependency between those. So you cannot, for example, run task 1 before the task 2 will be ready. So this is API. And those API is, TornadoVM is coming with the graph optimizer that is able to work with that API and the structures that the API creates. It works a bit like the database optimizers, query optimizers, because they know, okay, we have that many of tasks, we know the dependency between them, we can optimize them to run them in the best way possible, because we have all the context that is necessary. Then we have execution engine that is doing the proper execution. And what execution engine is doing is just splitting the workload between different hardware that is available. So if something is better suited to run on CPU, it will run on CPU. If something is truly parallel and can be run on the GPU and is properly created with the proper data structure, it will be run on GPU. So a lot of the intelligent logic is happening behind it. A lot of smart optimization. And then at the bottom, we have TornadoJIT compiler. That is based on the GraalVM compiler. It's an extension of the GraalVM compiler. That is, the screen there. That is just creating when it's deciding, okay, we need to have code for the GPU and FPGA, it's just creating the code for the particular piece of hardware. So very interesting project. A lot of interesting API. It's able to do managing memory because it's able to handle memory very well because a lot of optimization is happening there and it has own JIT and own virtual machine. It's just checking what is worth to be run, what is not. As far as I know, it's not that ready yet for the machine learning workload because there are still some missing pieces. However, guys are working on it to the level that they are currently created the company Paravox AI. That goal is to create the runtime that will be very good for the AI runtimes on the JVM. And if you want to learn more about the TornadoVM programming model, there is a very good article on Fujay exactly about that. It's very, very interesting piece because there's a lot of very smart optimization in the project. And the last one, we are wrapping up. Let's talk about the future, about the HAT and Project Babylon. What the HAT is? Oh my God, remote was lost. Okay, HAT is Heterogeneous Acceleration Toolkit that was announced on the last JVM Language Summit in 2023. Because, you know, there is a pressure on the market. Everybody wants to have machine learning, and a lot of people want to be able to root that machine learning with Java. Even me, whenever I'm talking with the customers, because I have the pleasure to do that, I hear, okay, we are just Java shop, we want to go full Java, however, the ecosystem is not ready, so we need to go Python. We don't want to go Python, please help. And JDCam people know that. That's why they are coming with the possible solution. And those solution is called Project HAT. And Project HAT is, okay, it's not the Project HAT, it's just the HAT. It's Heterogeneous Acceleration Toolkit. And most of the pieces I was describing today, they are in HAT, because we have ND-range API. So happy to create the ND-range by hand. We have ability to work with Panama, because Panama is very good to doing native calls, so we can just make the feeding the memory to the models easier. There is support for something you haven't heard of. Okay, there's also support for foreign function memory API, so ability to run the C code. However, also something that I didn't mention before, code reflection from Project Babylon. And what code reflections are? Code reflections are the extension of Java standard reflection, which allows to access to symbolic representation of Java code, such as method bodies and lambda expression at runtime. It means that is a reflection, however, happening on the runtime. So you can just do meta programming in Java. It allows you to rewrite the code on the fly. And in practice, it's working on something called code models. And code models are in the space between the abstract syntax tree that have all the information that's necessary to rebuild the program, and between bytecode that have the type flattened and is just the structure that is used to run the code very efficiently. Like I said, code models are there. They have their own special API that allowing traversal, and as you know the structure of the code, and you are in the runtime, so you know the hardware, you are able to rewrite it on the fly. And currently, it works like that. With JDK, we have information about the structure of our code, and we are able to create the vendor native runtime code, for example, for the GPU. And there are already first implementation doing that. There's Project Triton. There's a Triton language that was created for OpenAI that have open source language made for the GPU by the OpenAI. So probably one of the coolest things possible. And currently, it has code models, experiments, done by Paul Sandoz in Java itself. So that's the first, that's one idea they are trying to implement with the code reflection. And Babylon, so the project that introduced code reflection, is one of the pieces of the project HAT. Panama is the other, because, like I said, memory feeding data through memory is important. So we have great API for that, for off-heap memory. It's called memory segments that eliminate the need of manual memory management between JVM and GPU. And fact is, this is something that is happening right now. It's not something you can probably, there are demos. You can access because fortunately, JVM and JDK development is made in public. So there are already some builds you can run. I've tried, it didn't compile on my Mac. So probably I need I need to ask some questions. However, this year, in August, there was an update about the project is happening. So a lot is happening behind the scenes because, Java just feels the breath of all other languages that run on the GPU efficiently. OK, it was long, so it's time for the conclusion. I have 2 minutes, perfect timing. So where are we? Panama and Valhalla synced. It's incubator and ready to go in the same time. It's probably the most surprising part of the whole presentation, that something like incubator is already used in production. Valhalla have floats. They are delivered right now. However, unfortunately, they will probably deliver with the Valhalla itself. So do not know when. GraalPy, if you like to live dangerously, you can try it. It's a lot of fun. However, if you do not have many unusual dependencies. JCUDA works. Simply works. Most of the framework is based on it. Sumatra, what is dead may never die, because what is dead may never die, because it was never published, so it's probably still there. However, won't happen. TornadoVM, they are doing a lot of good work and currently going into machine learning. You already can run GPU-intensive code. They need to do some works to run it efficiently with the machine learning workload because they have their own characteristics, and probably HAT and Babylon are the future. What can I say? It was long. It was long for me. Like I said, 150 slides, but hope you like it. Yeah, and thank you. Waiting for your questions for the 1 minute more.
All systems are nominal. Initialize Genesis sequence.